Assalamualaikum warahmatullahi wabarakatuh. My name is AINAA NASUHA binti Mama Afandi. In this video, I will talk about Geography Information System in Landscape Architecture.
In Chapter 11, in hydrologic will likely emphasize the importance of terrain analysis and hydrologic modeling, whereas GIS user in wildlife management will be more interested in analytical functions dealing with wildlife point, locations and their relationship to the environment. In Task 1, introduce the buffering and overlay, the two most important vector data operations. The availability of overlay tools is varies in ArcGIS. User with the level license level have access to the overlay method of identity, intersect, symmetrical difference and union. User with the best standard level have the access to only intersect and union. They are limited to 2 input layers at a time. Task 2 let us use multi-part of polygon features in overlay operation. Both Fires 1986 and Fire 1992 are polygon layer derived from Boy's Fire. An overlay of multi-part polygons result in an output with few features record, thus simplifying data management tasks. In Task 3, we need to perform area interpolations and transfer non-population data from census tract to school district. In Task 5, we need to first select from AMSCEMT type PUB 24K points those sites that have the status of action complete, and then click the selected site that are within the Jefferson County. The final part of Task 5 is to convert the output shapefile into the KML file so that we can view that site in the Google Earth. In Chapter 12, in contrast with the vector analysis, which use point, line, polygon, raster data analysis uses cells and raster. In Task 5, we need to locate the potential habitats of plant species. The set value in STRMGD are the ID values of stream. The set value in ELVGD are the elevation zone of 1, 2, and 3. Both raster have the cell resolutions of 100 meters. The potential habitats of the plant species must meet the following criteria, which is elevation zone 2 within 200 meters of stream. In Chapter 13, to incorporate them into a variety of applications, slope and aspect play a regular role in hydrologic modeling, snow recover evaluation, soil mapping, landslide delineation, soil erosions, and predictive mapping of vegetation communities. In Task 1, the elevation raster PLN is imported from the USGS 7.5 minute DEM and have an elevation ranging from 743 to 1986 meters. The shapefile stream shows major stream in study area. In Task 2, it covers slope, aspect and surface curvature. First is to derive a slope layer, and second is to derive an aspect layer. Task 3 shows how to construct a TIM from an elevation raster to modify the TIM with a medium shapefile as a break line. We will also display different features of TIM. Terrain is a data format from a terrain mapping analysis in ArcGIS. A terrain is stored in the feature dataset of a geodatabase, along with other feature classes for backline, lakes, and study areas boundaries. In Chapter 14, a viewshed is an area that is visible from a viewpoint, and a viewshed analysis refers to the derivations and accuracy assessment of viewshed. In Task 1, we need to first create a hill-shape map of PLN to better visualize the terrain. Next, we must run the viewshed analysis without specifying any parameter value. Then we must add 50 meters to the height of viewpoint to increase the viewshed's coverage edge. Finally, we must run the line of the site operation. In Task 2, we need to digitize one more lookup location before running a viewshed analysis. The output from the analysis represents a cumulative viewshed. Task 3 shows us the process of delineating area-wide watershed using elevation raster as a data sources. Embedded stream.php serve as the reference. Unless specified otherwise, all the tools for Task 3 reside in spatial analysis to hydrology toolset. In Task 4, we will derive a specific watershed for each point in PowerPoint.php.
Chapter 17 cover least cost path analysis and network analysis, both dealing with movement and linear features. Least cost path analysis is raster based and has a narrower focus.
In task 1, we will use the same input as in the figure 74A and 74B to create the same output as in the figure 74D, 75A and 75B. Unless specified otherwise, we will use tools in spatial analysis tools from distant tool set. In task 2, we will find the least cost path from each of the two cells in the median path GD to the sources cell in peak grid. The least cost path is based on the path distance. Calculated from the evaluation raster, the path distance measures the ground and actual distance that must be covered between cells. Task 3 is to find the shortest route between two cities in the US city shapefile on the interstate network. The shortest route is defined by the link impedance of travel time. The speed limit for calculating the travel time is 65 miles per hour. In task 1, we will first examine the input data sets, then build a percentage database and the feature data set, and then import Moscow.shapefiles and selective TBF as the feature classes into the feature data set. We will use a network dataset built in this task to run a closest facility analysis in task 5. So in task 5, we need to point the closest facility. In task 6, we need to find the service area.